All right, so what I'm going to do is I'm going to start off and I'm going to think about this problem and read it again slowly. It's a cylindrical can. So I'm going to draw myself a little picture. And the dimensions that matter for a can is the radius or diameter, depending which one you want to work with, and its height. So there's my cylindrical can. Reading the question carefully, it says it has a capacity of 250 pi centimeters cubed. And it says that we want to minimize the amount of material. Okay, well, thinking about minimizing the amount of material means that I want to minimize the surface area of this can. So we want to minimize the surface area. Looking at the can, I've got a bottom, I've got a top, and I've got a curved side, and I think we talked about that on the Wednesday. So surface area is going to be the area of the top plus the area of the bottom plus the area of the curved side. Now, I write that out so I don't make any mistakes. The top is a circle, so it's going to look like that. The bottom is a circle, it's going to look like that. And the curved side, when you cut it and lay it flat, as we saw on Wednesday, looks like a rectangular piece, where this part is the circumference, so that's 2 pi r, and this is the height of the cylinder. So what happens is we cut this down and we lay this flat, and what you see is, maybe I can show you, if I have a piece of paper here and if I curl it up, you can see, I'm awfully close, but you can see that this all the way around is the circumference of that circle, and if I was to cut it and lay it out, that circumference actually becomes its length. Maybe a smaller piece of paper will help. Let's see here. So there we go. That's my circumference. Okay, we cut it and we lay it out flat, and you can see that this part is the part that makes up the circle, the outside of the circle, the circumference. So there you go. All right, so this is going to be given as the area is pi r squared for a circle. Pi r squared, top and bottom are the same size, otherwise the can isn't going to fit together very well. And this is 2 pi r times h. So what we have is a formula for surface area in terms of two variables, r and h. And I can simplify it up a little bit. I've got pi r squared plus pi r squared, so that's 2 pi r squareds, plus 2 pi r h. Now, since optimization, I think, is just an application of curve sketching, and if I wanted to sketch this curve, I'd have a problem. I'd have two variables in here. That's going to give me a bit of a problem for curve sketching. I need it in terms of one variable. So I'm going to refer to this as equation 1, and I'm going to stop and I'm going to say to myself, well, I need to equate r and h. Now, I don't think I've used the word equate before. I think I've said I need to determine r in terms of h or whatever, but no big deal. So I go back to the question and I find another piece of information that I haven't used. I notice capacity here. Capacity is going to work with volume. So the volume of this circle is going to have to, or this can, is 250 pi centimeters cubed. And volume for a regular solid using the pancake method would be the area of the base times the height. So it's the area of the base, which is pi r squared, times the height equals 250 pi, getting rid of units. Isolating for h, we get h equals 250 pi over pi r squared, which is simply going to be 250 over r squared. I'm going to call this equation number 2. This is kind of a separate sort of logic, and we're going to plug it back in. So we're going to sub equation 2 into equation 1, and what that's going to do is give us surface area in terms of one variable now, r in this case. So it'll be 2 pi r squared plus 2 pi r. Now instead of h, we're going to plug in our 250 over r squared. Okay. making this look a little bit nicer. Now r over top of r squared, that's going to reduce to give me r to the negative 1, or 500 pi over r. And notice here, we have a restriction on our variable. R cannot equal 0 in this case, so that makes me think about intervals. I wonder what is going to happen with the interval of the variable r. So I know that if r is 0, then there's no can, and if r is negative, it doesn't really make sense. So we know that r has got to be greater than 0. You also know that h has to be greater than 0. So take a look at h in terms of 250 over r squared. R can get smaller and smaller and smaller and smaller and smaller, which is fine because that means that h is going to get bigger and bigger and bigger. What happens if r gets bigger and bigger and bigger? Well, no matter how big r gets, 250 divided by a really, really big number is never 0, and it's never negative. It's just going to get closer and closer and closer and closer and closer to 0. So h must be greater than 0, can't be negative, can't be 0, but r certainly has no upper bound. It's going on to infinity. It can be as large as we want and everything stays kosher. So this is what we call a bounded interval. It's bounded on one side by 0, and it keeps going. So we're not going to have any endpoints, so we're not going to want to solve it by looking at endpoints. Well, not solve it, but prove the maximum minimum using endpoints. So we're going to want to use intervals or the second derivative test, depending. So I'm back down here now. I'm thinking about this. I want to find the critical values. This is curve sketching, right? So what I want to do is I want to find the first derivative critical values, because those will be places where the slope of the tangent is 0, and that's going to be places where it can be changing from increasing to decreasing or decreasing to increasing. So we're going to determine the derivative. That'll be 4 pi r minus 500 pi r to the negative 2. That's my derivative-friendly form. That's a nice way of having it if I'm going to take its derivative again. 4 pi r minus 500 pi over r squared is an equivalent way to write it. And 4 pi r cubed minus 500 pi over r squared is our solving friendly form. Okay? And that's an equivalent way of writing it as well. Just a moment, I need to take that, and I'll be back to finish this example.